So we want to take a look at the first problem, which is how we find roots of complex numbers. And what I want you to notice is the formula, okay, from the book. What we do first is we write our original number in terms of a complex exponential. Okay, and I usually don't put this part on. Okay, I usually just write it as this. And then if you take the nth root, notice what happens is you take the nth root of the radial part, the modulus, you divide the original argument by n, and then you add on another term. Okay, and so k here goes from 0 to n minus 1. And you can convince yourself that if you raise this to the nth power, you'll get back this number right here. Okay, so let's see how this works. So first we want to take the third root of -1. So the first thing I'm going to do is I'm going to write this as a complex exponential. Okay, so I know that -1 is 1. This has a length of 1 times e to the I pi. Okay, you can convince yourself that's true by using Euler's formula. So notice here, theta naught is equal to pi, n is equal to 3. So I plug this into the formula. Okay, the cubed root of -1 is the cubed root of 1. That's this part right here. This is the cubed root of r naught, which is 1. And then I'm going to have this exponential term where I divide my original argument by 3, and then I add on this 2 pi k. I'm always going to have this part divided by n. Okay, where this can go from 0, 1, and 2. And when I don't have, when the root isn't very large, like 2 or 3, I can work out the different cases, all right? So if I let k be equal to 0, I just get e to the I pi over 3, which by Euler's formula is cosine of pi over 3 plus I sine pi over 3. I'm going to use this unit circle. This is something that you want to get to know or be able to work out. And I know that for pi over 3, the cosine is going to be 1/2. Sine is going to be square root of 3 over 2. Okay? And now I can go ahead and I can look at k equal to 1. And I'm just going to get 2 pi over 3 plus pi over 3. So that'll give me e to the I pi. When I use Euler's formula, cosine of pi plus I sine pi, that's just going to be -1. And we know that's true. We know that the cube root of -1 does have a root of -1. And finally, when I let k be equal to 2, I'm going to get 4 pi over 3 plus pi over 3, which is 5 pi over 3. And when I use my unit circle, I find out that's 1/2 minus square root of 3 over 2i. Now, we're going to use a trick to get larger roots, like 4th, 5th, 6th. One of the things you want to notice is that the roots are always uniformly spaced. Okay, if you look at these 3 roots, once I know this root here, okay, the other root's going to be 2 pi over 3 away. It's going to be down here. Okay, so these roots all differ by 2 pi over 3. Okay? And so I can see that these are going to have the same x coordinate, but the y coordinate is going to change in sign. Whoops, that should be square root of 3 over 2 here. Okay, so now let's go ahead and use this on a problem that's a little harder. So now we want the 6 roots of 8 to the 1/6 power. Notice that we're always going to have as many roots as we have. We're going to have as many roots as the order of the root we're taking. So if we're taking the 6th root, we're going to have 6 roots, okay? Okay, first thing I'm going to do is I'm going to write this in complex exponential form. So this will be 8 times e to the I 2 pi. That's my theta naught. My n is equal to 6. So now I'm going to use my formula. My formula tells me this is going to be the 6th root of the modulus, which is 8. And I'm going to divide theta naught by n, and then add 2 pi k over n. where k can go from 0 to 5. Okay? And when you look at 8, 8 is 2 cubed, so I can use a little factor. I can use the fact that 8 is 2 cubed. So when I take the 1/6 root, I get 2 to the 1/2 power. Okay? All right. Now notice that this is really difficult going through cases. You don't want to go through 5 cases. So what I'm going to use the fact that I notice every time I'm incrementing by pi over 3. So I start off at pi over 3, and then I add pi over 3, add another pi over 3, another pi over 3, and another pi over 3. And finally, a final pi over 3. And I have my 6 roots, and they're all equally spaced. Now, why do I like that? Because you notice that if I can get one of these solutions here, the other one is the same, but the y component's just going to change. And if I get this one here, the y component's going to change there too. Okay? So you notice that if you look at k equal to 0, okay, this is going to be k equal to 0, I automatically get this one too. I get k is equal to 4 when I go around 1, 2, 3, 4. Okay, so these are these two roots right here. And when I look at this root, I automatically get this one for free. So this is k equal to 1, so this is going to be k equal to 3. Okay. I just put in cosine of 2 pi over 3, and I find out that it's minus 1 over the square root of 2, and here it's positive square root of 3 over 2, but this other one can be negative square root of 3 over 2, and I multiply by the square root of 2. Okay, finally I notice that these two are just negative 1 and 1, right? So this is going to be equal to k equal to 2, k equal to 5, plus or minus 1. And those are my 4 roots. So it's kind of good to get used to this symmetry, the fact that the roots, you're always going to have, if you take the nth root, you know that z to the 1n will have n roots, and they're going to be spaced by 2 pi over n, okay, equally spaced. That's a really nice trick to know. Okay, we'll do problem 2 next.